Okay, this is the Math Models Unit 9, Lesson 3 video. This is going to be taking the exponential growth and decay models that we learned about in the last two lessons and kind of give us some application of those kinds of models. So they're going to be giving us situations where we have a growth and decay model and we're just going to be answering some basic questions about them. Some of this will require some calculation, but most of it is more or less just using what we learned in the last two lessons. So a herd of buffalo began with a population of 75,000. The average birth rate is 28% per year, but the death rate has been 43% per year. What is the difference between the birth and death rate? Okay, that's pretty straightforward. We're just going to do 43 minus 28 to find the difference. Difference means subtraction. And so you feel free to use a calculator for that, but 43 minus 28 is 15. That's pretty straightforward. So H is the population in a state of growth or decay. Very simple. If the death rate's higher, it's decay. If the growth rate's higher, or the birth rate is higher, it's growth. So this is decay because the death rate is higher. So we're going to do B. So that tells us something already. It tells us that the of our two equations, we're going to use the one that's decay. Remember that if the number here is larger than 1 point something, that's growth. And if it's less than 1, then it's going to be decay. So we already can see that when it asks us what the model is, it's got to be E, because that one represents a model where there would be decay. So you can see how these questions kind of lead one into another. And then the last one, according to your model, what will the population of buffalo in this herd be in 10 years? So we need to take this formula, and we're going to go to our calculator here. And we're going to take the one we chose, 75,000 times 0.85 raised to the 10th power. Remember, to do raised to, you can do shift 6, or you can shift and then the 6 key, or you can use this button right here, and then 10 years. So we can see it's down to 14,000, which, there it is right there. Answer choice C. So that's what you do on that one. Same exact idea on number 2. I'll let you do that one on your own. And pretty much the same idea on, I'll come to number 4 in a second. Let's do number 3. So for number 3, in 1970, a rancher stocked one of his ponds with 200 catfish. The following table shows how the population grew. Write an exponential equation modeling the population's change over time using your graphing calculator. So we're not going to use a graphing calculator. We're going to use the Desmos system, and we're going to use the exponential graph that we'd done previously. So I'm going to go to exponential regression. I will put a link in the video description. And if you'll remember, we are looking at, this is going to be L1 or X, and this is going to be Y. So remember, notice they say subtract 1970 from the year. In other words, we're going to consider this year 0. So it'll be 0, 5, 10, 15, 20, and so on. So we're going to go over here and do that. So enter our X's, 0, 5, 10, 15, 20, 25, 30, 1, 2, 3, 4, 5, 6, 7 values. Yep. And then we'll enter these values in the Y. So 200, 322, 519, 836, 1,346. So you're just entering these in this way. And 2,167 and 3,490. Already it's graphed a model for us. A couple things to notice. Here we have the 0 point. And then I'm not sure what this point is for, but those are the different points from the actual equation. So we have, notice it crosses 0 at 200 because that was the starting amount. It asks us for a model. So we should have known that 200 would be here because that's the starting population. But if we go over here, see the parameters that say that we have 200, and then we have 1.09 as our B, or pretty much close to 1.1. So you can see the only one that even gets close is going to be right here. Because it's growth, it has to be greater than 1. So already before we even did that, we could have eliminated, let's see, that's decay. That's 122 times as much. That's decay as well. So it had to be one of these. We just needed to know what that B term was. And so we can see it's this one right here. So that's pretty much what you do there. I'm just going to check these other ones. All right. You can do number 5, use the same concepts that we used up here. But I do want to talk about number 4. So number 5, you can do on your own. 1995, wildlife biologists found that any given hour on a particular beach, there were 5,750 mosquitoes present. They also found the population was tripling each year. So this is an important concept. Tripling means 3. So 3 times, we know that. But when we're talking about a growth model, unlike these ones previously where we had an increase from 1, these are actually going to be all the way up to 3. In other words, it's going to be 3 raised to the power as opposed to what we've been doing so far. So right away, I can tell you right now, we're looking at A, because that 3 right there is what I'm looking for. The starting population is 5,750, and then there's a 3. After that, you can do this easily yourself. You want to know 2008. So that's 13 years later. So you're going to use 13. And you're going to put 13 in for T in this formula and solve. So you can do that one on your own. And that gets us through this lesson.